Okay, this is the simulation for the wavelength of light lab, and essentially what we would normally do is we would shine a laser beam, a monochromatic source of light to be technical, onto two slits. These two slits then act like sources, proving that light is definitely a wave, not a particle, and it will constructively and destructively interfere with itself. When the light has a similar path as we have right here, then we're going to have a bright spot. Right up here, then there's going to be a spot where there's a dark spot where the light is destructively interfering, and then there's going to be bright spot, bright spot, and so on and so forth. On the other side, we have corresponding dark, bright spots. So if we were to travel one full wavelength further, then we're definitely going to have a bright spot. If we were to travel lambda over 2, then we're going to have a dark spot. So what we can do is we can say, alright, we know in the center we have a bright spot, and then we're going to have a dark spot, and then we're going to have a bright spot when the light has traveled exactly one wavelength further. We can mumble something about similar triangles and say that the wavelength divided by the distance that these slits are separated has to be equal to x divided by L, where x is this distance just right here, and L is the distance between the slits and the screen. We can then go ahead and calculate what the wavelength is. I trust your algebra is good enough to do that. Then we're going to go ahead and we're going to pop open the simulation, and we're going to mess around with the wavelength and then the slit separation. So I'm going to start you off by using a red laser and just take a look at how the slit width is going to affect this. I'll kind of show you what I expect you to kind of draw with this guy. So here we have the laser. You can tap on that and change the color. We want to use the wavelength. You can tap on this and mess around with the slit separation. You can see it changing right there. And you can also drag this guy around. So if I were to go ahead and do this, I would come down here to the 10 centimeter mark. That's going to be the quote-unquote center. And I would personally draw a really bright, intense thing, and then a dark spot, and then a bright spot, dark spot, bright spot, dark spot, bright spot, dark, and so on and so forth. We're technically seeing a both interference pattern and a diffraction pattern grouped together. So for this particular guy, I would say that the base position is going to be 10 centimeters, and I'm going to have my really big bright spot, and then a dark spot, and then a bright spot, dark spot, bright spot, dark spot, bright spot, dark spot. And then on the other side, I would draw something that's going to be symmetrical. What I'm really interested in is how much are these guys spaced out? So how spread are they? As you mess around with the As you mess around with the separation, kind of pay attention to how narrow or not narrow that guy is. Then all I'm going to have you do is I'm going to have you pick your favorite distance and start out with the red laser and measure the distance and measure the length to the screen. Then go ahead and measure the distance to the leftmost peak and the rightmost peak, so we're looking at the first bright spots, and you're going to average those to get a value for x. Then you can go ahead and calculate what the wavelength is, and it darn well better fit in that for red light. I'm going to have you repeat the process for both green and blue light.